Our key goal when building machine learning models is to make them generalize so they produce accurate predictions on unseen examples. So that is, we want to reduce the generalization error, the difference between performance on the training set and the validation set. And we call any technique designed to reduce the generalization error of a model regularization. So let me show you some of the fundamental regularization techniques that you should know about. So firstly, poor generalization is caused by overfitting, and overfitting is symptomatic of overly complex models. You can see that here that one of these models is clearly overfit because it has a very high capacity. And because of this, probably the simplest way to regularize your model is to reduce its capacity and use a simple model, something that can't represent something so wild. In the case of this polynomial, it would mean using a lower order polynomial that doesn't look so crazy. Weight decay encourages your model to be more simple without having to decrease its capacity. And it does this by making the model weights smaller. So let me get into exactly why that works in a second. But firstly, we implement weight decay by adding a penalty to the loss function. The form of this penalty is a parameter, lambda, which is known as the regularization factor, which controls how much the model is simplified, followed by the norm of the model weights. So firstly, what is a norm? Well, a norm on the weights of our model is a mathematical term that gets larger as the weights get larger. Here, what you can see is a few different types of norms. I've got the LP norm, the L1 norm, and the L2 norm. Mathematically, what we would call the LP norm is where you take a vector, raise the absolute value of each element to the power of a number, p, sum them up, and then take the pth root of that number. In our case, that vector will be a vector of all of the model weights. So given that p could be any number, we can look at specific cases like the L1 norm and the L2 norm. So the L1 norm would be equivalent to taking the sum of the model parameters, and the L2 norm would be equivalent to finding the magnitude of that parameter vector. You'll see them written as that vector that you want to take the norm of, with two vertical bars on each side and a subscript indicating the value of p. And the L2 norm is used so frequently that the subscript is often omitted, and it'll just be referred to like that. So on the right hand side, you can see kind of diagrams of what the L1 and the L2 norm might look like in one-dimensional parameter space. So the L2 norm is a quadratic graph, and the L1 norm is just a absolute graph showing the absolute value of the weight, regardless of whether it's positive or negative. And what we're going to do is we're going to add these surfaces to our loss surface. Each of these norm penalties has a minima at 0. So they pull the minima of the loss surface towards 0 too. When you add them together, it might look something like this. So we've got the original loss function on the left, an L2 norm penalty, which is this quadratic bowl. And then adding them together, you can see that now the regularized loss looks different. And the lowest point on that is much more close to the origin. The regularization factor that I also talked about, lambda, that scales up and down the strength of the regularization. So graphically, that would be scaling up the vertical height of the regularization term's surface. So why does this work? Well, one way to think about it is that overfitting is when your model has high variance. And that means that there's many different parameterizations which perform equally well. Regularizing the loss surface puts a preference on those parameterizations whose parameter norms are close to 0 when you're using this kind of weight decay. Another way to visualize it is that each of these weights effectively determines how much influence a particular feature has. It's helpful, I think, to consider the parameter values in the limit when they're equal to 0. And in that case, any change in feature is going to have 0 influence on the output. So the model will predict the same thing everywhere. That's a very simple model. As you allow parameter values to move away from 0, each feature can exert more influence and change the shape of the function more. These norm penalties help by reducing how much each feature changes the output by reducing the weighted influence and pushing those weights towards 0. Typically, we use the L2 norm penalty. This formulation of the loss function is commonly called ridge regression. And there's a few different ways to write out that L2 regularized loss, as you can see there. Alternatively, you can use the L1 norm penalty. And that's just a case of summing up all of the parameter values in your model and then multiplying them by that regularization factor lambda. So when would you want to use which one? Well, let's think about the way that they influence the parameter updates when using gradient descent, which is how most of our models are going to be trained. The gradient of the regularized loss function is going to be equal to the gradient of the original loss function added to the gradient of the norm penalty. And that gradient really indicates the strength with which the parameters are pulled in that direction. The L2 norm penalty is, it's kind of flat right near the origin, and it gets very steep far away. So what it does is it pushes down large parameters very strongly, where it's very steep, away from zero, but it barely affects small parameter values. But the L1 norm penalty is the same steepness everywhere. And what that means is that regardless of what parameter value you're looking at, it's always going to pull the parameter towards zero, regardless of that parameter's size. Unless the gradient of the original loss function pulls strongly enough in the other direction, the parameter value will be pushed all the way down to zero. And the only reason that the original loss function would pull in the other direction to counteract that norm penalty pulling it towards zero would be that the original loss function is reduced significantly enough by changing that value and pushing it away from zero. So as a result of that, if the parameter doesn't affect the original loss, then it'll be pushed all the way down to zero by that L1 regularization. And so that L1 regularization can be used as a form of feature selection, because it will tell you which features don't affect the original loss function, as their corresponding parameters will be pushed all the way down to zero. And then you can remove these and save memory and compute when you're using your model. The L1 regularization is also known as Lasso Regularization, so you might see that around. You can also use what's called elastic net regularization, which is a simple mix of both ridge and lasso regularization, and that includes a parameter which weights the importance of each. So you can do both L1 and L2 at the same time, just weighting off which one's more impactful. So one thing that you should be careful of is that you should not regularize the bias of the model. That's because constraining the bias doesn't make the model simpler, which is exactly the point of weight decay, to make the model simpler. Regularizing the bias just makes the model prefer passing through the axis closer to zero, which might not be what the true data generating function looks like. And that's exactly what I've tried to illustrate here. I've got a model which only varies by one parameter. It can only move up or down. It's always the same wavy shape. But if we were to regularize that parameter would be pushed towards zero, even just a little bit. But when we do that, it just gets more wrong. It doesn't actually simplify the complexity of the model and make it less likely to overfit. Another thing to note is that the regularized loss does not tell you how good the model is performing on the data. It tells you how good the model is at performing well on the data and minimizing the norm penalty at the same time. So that's what the performance tells you about. It's the combination of those two things. So once the model's trained using the regularized loss function, what you want to do is evaluate the model's performance on the data using the unregularized performance measure. So here's how I'd go about implementing L1 or L2 regularization in code using sklearn. I simply imported ridge and lasso from the linear module of sklearn that I've loaded in the Boston dataset just as an example. And then you simply specify that you want to create an instance of the lasso or the ridge regression. So this is L1 and this is L2 regularization. And then you can pass in what they've called alpha. I called it lambda, which was the regularization factor. So you can specify that here, and that's a hyperparameter, which you would probably need to tune. Another regularization technique that you can use is called early stopping. So here's a diagram of early stopping, and what early stopping is where you stop the training before the training loss converges. Instead, you stop the training when the validation loss stops reducing and begins to increase. So that is when the model begins to overfit. In practice, what you'd do is you'd save your model every so often in checkpoints like that. And then after training, pick the one which achieved the best generalization error, which you have saved, which here would be checkpoint 2. And you can see the ideal stopping point is the one where the validation loss is lowest, and that's the generalization error is lowest. But beyond that point, you can see that the validation loss begins to increase, and that's an indication that the model is starting to overfit. So here's how I would implement that in sklearn. Firstly, I'm just gonna try and look it up. So sklearn linear regression early stopping. All right, we're looking for a model. So that looks like a tutorial on how to plot it. This looks like a model. So let's check that out. So what is this? This is a linear model fitted by minimising the regularized empirical loss with stochastic gradient descent. So this simple linear regression model uses the analytical solution to optimize the parameters. The simple linear regression model that we've already seen in sklearn uses the analytical solution to optimize the parameters. But the analytical solution is unsolved until the moment when the calculation completes, at which point you have the parameters that give optimal performance on the training set. So as such, you can't see its performance over time, which is what we need to be able to see to implement early stopping. That means that you can't plot the loss curves, and so you can't evaluate the generalization error periodically. So that tells us that we can only use early stopping for models which are trained iteratively. So before we use this Sgd Regressor, I just want to show you some helper functions which I've got written out. One of them just creates some fake data, and then it splits it up, scales it, and returns the training and validation sets. One of them uses that data to train a model for a bunch of epochs. It takes in the model, it creates that data, then it's going to fit that model, make a prediction, get the performance metric for both the training and the validation set, and then it's going to add them to a list. And we're going to implement this so the Sgd model comes in, and when we call this fit method, it just makes one optimization step. So each of these training errors that we're adding to our list will be a list of the training errors as it progresses through time, as it gets optimized further and further. We also plot a horizontal dotted line at the lowest validation loss, so we can tell where that was. So here, we use this different version of the linear regression model in sklearn called Sgd Regressor, which is a linear regression model which is optimized iteratively using gradient descent. So you can see the different parameters that it's got here. A few of them that I'm going to use, I'll show you them in a second, is the max iter, which is number of passes over the training data. I'm going to use the warm start, which says reuse the solution of the previous call to fit as the initialization. So I can call that fit over and over again and pick up where I left off from last time. And we're going to use this tolerance keyword argument. This is the difference between the train and validation loss, which will stop training out. So let's see that in the code, what I've done here. I've simply imported that Sgd Regressor, created an instance of it like we would create a linear regression model, passed in those keyword arguments, max iter equals 1, so it only takes one optimization step. The tolerance is negative infinity, so it's only going to stop when the change in loss is less than negative infinity, so it's basically never going to stop. So I can continue to train it, and I can see the performance even as it increases beyond the point where it should have stopped if I was stopping early. And then we'll specify warm start equals true, so that when I pass it into this function and I call fit over and over again, it just picks up where it left off last after the last fit call. And then down here, I've run this before and got quite a nice graph, so I'll keep it with that one. I won't run it again, but here you can see the training set loss and the validation loss over time. And what you can see is that around about 40 epochs, it gets the best validation loss, and then it begins to rise up slowly again. And so this is the point where I would want to hopefully have checkpointed a model nearby, maybe in one of those epochs around there, and then I would use that as my best model, because that's the model which I know has the best generalization performance. It performs best on the validation set. So this is obviously a toy example for a few reasons. Firstly, we're not doing any mini batch gradient descent as we usually would. We're doing full batch. Secondly, we're evaluating the model on the validation set every step. So for a large model and a large validation set, that could be really computationally expensive to compute, and it could just take a while. So in practice, like I've said, we do something more like check the validation performance every 20 epochs, and then depending on the size of the data set and the model, we basically set that, how often we check it. And then, importantly, we'd save a version of the model at that checkpoint every 20 epochs. And after the training process is run all the way, probably to the point of overfitting, we can look at the training curves and identify which of our saved models would have resulted in the lowest generalization error. So there's many other types of regularization too, but we'll save those for later. And for now, you should have a rough understanding of how we can improve the generalization ability using regularization. We can do that using what I've showed here, which is reducing the model capacity, introducing penalty to the loss function, and changing the point at which we stop training.